Hello students, welcome to this video lecture. And now, as I promised in the previous lecture, we will see another way of dealing with integration. So earlier we were doing indefinite integration. Now we will see definite integration. So I would like to highlight few things before coming to any theorem. Let us suppose that fx is a function which is continuous in the interval, closed interval a comma b. Now you don't have to think much about this word continuous. It is a mathematical term and there is mathematical meaning associated with this. But for now you can understand that if you draw the graph of this function, there is no break. There is no break basically in the graph of this function. For example, if you draw a function like this, it is smoothly going on, there is no break. So if you take a point A and a point B, so it is a continuous function in this interval. But if you come across some function like this, that it is a function like this. So here if we take the interval A to B, so at some point C you can see that there is a break in the graph. There is a discontinuity. So here what we have to only understand that any function which we are taking here is small of fx, that is actually a continuous function in a given interval. So now if I take another function capital Fx and I say that this capital Fx and this is small fx is related with this relation, that if we differentiate capital Fx with respect to x, I get small fx.
Okay, so can we understand this concept by using some example? That would be better for a student to learn the concept with some help of some examples.
Right. So basically what we can do here, that we can take a function fx, suppose let fx is equal to 2x. Let us suppose fx is 2x and capital Fx is equal to x square. So I am also taking an interval, so there is no need right now, it is already continuous everywhere, still we are taking. So I can say that this function fx is equal to 2x is continuous in this interval 1 comma 3. And this capital Fx is a function which I have taken, and if I see that if I differentiate this x square with respect to x, which is actually the capital Fx function over here, so it will give you 2x, which is the small fx. So
previously we have learned indefinite integration, and now here we are going to deal with the definite integration.
Definite integration.
So is there any relation also, or we can understand these two by relating by somehow?
There is a relation between indefinite and definite integration. So I'll just come to that. Since we have seen this relation here, so I will first tell you that there is a theorem in calculus which is called fundamental theorem of calculus. So if you come across the concept of calculus, so this theorem itself is called fundamental theorem of calculus. What it says actually, basically the functions which we took earlier, fx and capital Fx, and we said that capital Fx when differentiated gives you a small fx. So this fundamental theorem of calculus says, and x is continuous in AB interval. So it says that if I take the integral of fx, the small fx, so it is very easy right now if you have seen the previous videos, that when differentiating this you get this. So when you integrate this you get.
That is why we have said that the integration is the inverse of differentiation.
Yeah.
And this is how it is related.
This is how it is related. So if you are differentiating this, you are getting this. So if you integrate this, you will get f of x plus a constant of integration, which is
indefinite one we have learned.
Yeah, that is the indefinite one. But the fundamental theorem of calculus highlights something else. It says about definite integration. If I take the interval a to b, where this function is continuous, then this value comes out to be FB minus FA. This is what is definite integral and its statement. Now, how can we compare the definite and indefinite integral? That is actually the point here. So if, as I have written earlier, that integral of fx is capital Fx plus c. Now what we do actually, when we put the limits, this is called the lower limit, this is the upper limit. So when we put the limits, we actually integrate this as we do in indefinite integration, and then we put the limits a and b.
Okay.
So when we put these limits, that means we are saying that x is having a value b here. So we put the upper limit fb, and c is a constant, so b has nothing to do here. Minus, we'll take the lower limit, that is fa plus c, and we'll see that this c and this is minus c, which cancels. So this becomes fb minus fa. So this is what the fundamental.
So if we can sum up this thing, the difference between indefinite and definite is mainly that in indefinite we have a family of curves. There are several functions that can represent the same thing. But here the value is exact.
Yeah.
That is why it is called definite.
It is called definite.
And indefinite means there are various functions that represent the same thing. Here.
Yeah.
Okay.
So this is mainly definite answer is coming out.
Okay.
FB minus FA. Even there is no x over here.
Okay.
The variable of integration has also vanished. So there is a fixed value which is coming over here. So basically, if I take an example as I have taken earlier. So
we can solve the same example by using the concept of definite integration also.
yeah, any example which we have done by indefinite integration, we can do it by definite integration also. Just say here we took as 2x is the function, and when we integrate it from 1 to 3, we get the capital function. When we are not putting the limits, then it is capital fx basically. That is the integral of a small fx, because the derivative of capital fx is small fx, just anti-derivative thing. But when we put the limit here 2x dx, and suppose I am putting the limit 1 to 3, so in that situation what we get here, the integration of 2x, we all know till now is x square, so we'll simply put the limit 1 and 3. So this will become 9 minus 1, which will be 8.
Okay.
So this is an example which elaborates that how can we get a definite value of an integral if the lower and upper limit is given to us.
And this is a very general situation in physics. In physics generally, whenever we are integrating, we generally have the end values, that is from where we have to start and from up to where we have to end there. So I think this is going to be a very useful concept when we apply this thing in physics there.
Yeah, in application of physics, basically definite integral may play more role than the indefinite integral.
Mostly we have given values or set of values between which we have to integrate a function.
Yeah.
Okay, so can we apply the method of definite integration to some other function also?
Yeah.
Different type of functions can be applied there.
Yeah, like this is an algebraic function,
yes.
2x. So if I want to apply it in trigonometric